Okay, so hello and welcome back. So in this video we want to talk about the limitations of mean deviation. So we have talked about the mean deviation about the mean. The mean deviation about the mean, and we have also talked about the mean deviation about the median. About the median. Okay, so we talked about these two concepts, and basically the main part of these two concepts is the mean of your observations and the median of your observations. And you know what the mean is, and you know what of course we're going to talk about these two in just a few moments. But then the mean deviation about these two is basically the same idea, that you take all of those distances of all of your observations from, for example, from the mean or from the median, and then all of those distances, you get the mean of all of those distances, and that becomes the mean deviation from the mean or from the median, meaning that how much are basically those observations deviating from what sort of distance they have from the mean or from the median. And then when you take and then in the average or in the mean, you will get one single value, and that single value is representative of how is kind of a representative of how all of your observations are behaving on average altogether. Now, but the problem here is that basically all of these two ideas are based on mean and median inherently have some problems, meaning that these are merely two methods that we have devised in order to find the mean deviation about the mean or the mean deviation about the median. As long as in a particular situation they are useful, of course you can use them, but in some situations, basically based on their relative and inherent limitations, they cannot be used. And that comes in with any sort of method that you would devise, because any sort of method that you devise automatically brings in limitations. For example, suppose that you devise some method or some technique to draw water from a well, or from some particular well, for example. Now, when you devise this method or this technique, and when you actually build all of the things that you need to build in order to mechanically, in order to basically draw the water from the well, then what happens is that then you're limited to only drawing water from that particular well. Of course, assuming that your construction and all of the gadgets that you have and everything is well placed, put into place, and then you cannot move it anymore. So then you're limited to basically drawing water only from that particular well. If there is another well beside that particular well, you cannot draw water from the other well. Or if there is another well on the other side of the particular well, you cannot draw water from that either, and so on and so forth. That means that any sort of method that you devise is going to bring in limitations with itself. But again, there is another consideration, which is that as long as you want to do anything, you have to devise some method. So this kind of this limitation that is brought in with any sort of method or technique is the necessary evil. Otherwise, if you don't have a method, of course you cannot do anything. Anything that you want to do needs some sort of method, and so, I mean, as long as it's scientific, it needs some method, and so we are always limited to the limitations of the system that we are using. And so of course, based on that, for different kinds of things, or for different kinds of tasks, we use different sorts of systems, or different variations or different versions of the same system. So, and that's basically how the whole world is made. Basically, there is no other way of doing anything in this world. So now, going back to the concept of mean and median. Now, first of all, we need to understand what the mean is, and basically, based on the definition of the mean. For example, if you have some numbers like, for example, 1, 2, 3, 4, 5, and 6. Let's say that you have these numbers here, and the mean of these numbers is going to be, if I have these numbers on a number line, then the numbers are 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and 6. The mean of all of these numbers, your x bar, is going to be equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6, divided by the number of those numbers, which is equal to 6. Now, the sum of these numbers is 6 plus 4 is equal to 10. That's 21/6, which is equal to 3.5, which is equal to 3.5. 3.5 is your x bar, which, as you can see, is actually exactly halfway between your minimum and your maximum. Halfway between your minimum and your maximum. So that's basically how the mean behaves in this particular case. 3.5 is equal to x bar, and this is your minimum, and this is your maximum. Now, suppose that the data that I have here is particularly specific, because your data starts from, for example, a 1, and then you add a 1 to that, and then you add the 1 to the next number, and to the next number, and so on and so forth. And then based on that, of course, based on this particular characteristic of your data, the mean is exactly halfway between the minimum and the maximum. Suppose that I have some data, for example, like 1, 2, 3, for example, 1,000, 2,000, and 3,000. Now, this data, if I were to depict it on a number line, that would look like something like, if I take this as for example, as 1, then I would have 2 over here, I would have 3 over here, or let me basically, I cannot do it this way. Let me say that, for example, this distance is taken as the 3,000. Then halfway between that would be 1,500. Then halfway between this would be 750. Then halfway between that would be 350, 375, for example. And so on and so forth. And so, of course, then 1 and 2 and 2 and 3 would be these points, for example, over here, of course, much closer to 1. These would be 2 and 3. And the mean of your data here is x bar is equal to basically 5,000, 6,006, 6006 divided by 6 would be 1000, let me see, 3000 plus 2000 plus 1000 plus 6 is equal to 6006 divided by 6 is 1001. Divided by 6 would be 1001, and 1001 would be somewhere over here. So let's say that basically if this is 375, so 750 plus 375 is 750 plus 375 is equal to 1125, which would be this point over here. And well, then your x bar, which is 1001, would be probably, I don't know. So this distance would be, for example, halfway between 375 and 1, which is basically 376. Of course, I think my numbers are a little bit off, but that's not a problem. 376 divided 376 divided by 2 is 188. So that means that half of this distance is 188. So 750 plus 188 is 938. So this point would be 938. So your x bar is going to be somewhere over here. Somewhere over here, we can assume that this is 1001, which is your x bar. So as you can see, as I made these numbers, as I made these three numbers on the far right side weightier, the mean actually moved from the midpoint. So this point over here is actually the midpoint. This is the midpoint of basically the minimum. So this is the minimum, and over here this is the maximum. This is the maximum, and this is the midpoint of the midpoint of my observations on a number line. So as I made these numbers weightier, what happened was that basically then the x bar or the average of my data moved towards the numbers that were actually less weightier than these weightier numbers, right? And of course I can keep doing the same thing, meaning that, for example, suppose that I pick my data in such a way that, for example, I have 1, 2, 3, and for example, I don't know, 8,000 and 9,000, for example, and 10,000. This is my data. Now again, if I depict this data on a number line, what I would have is that let's take this as a 1, and let's take this as a 10,000. So that is 10,000. One half of that would be 5,000.5, which is halfway between the two numbers. Let's say that this is 5,000.5. These numbers are not actually between exactly. There is some 0.5, or they are off by 0.5 or something like that. But you get the idea from here. I made a mistake. I didn't add the 1 when I was calculating these numbers, but that's not a problem. Now halfway between these numbers is 5,005, and then basically halfway between 1 and, for example, 5,000 is 5,001.5. So 5,001.5 divided by 2 is 2,500.75. 2,500.75. And of course 1 and 2 and 3 would be these numbers over here, and then 8,000, 9,000, and this is supposed to be, of course, a 10,000. would be some numbers over here. Now it's not important where these numbers are. They're going to be somewhere over here, right? And this number over here is halfway between, on the number line, is halfway between I mean, as far as the value of the number is concerned, is halfway between your minimum, which is 1, and your maximum, which is 10,000. So this is the midpoint as far as the value is concerned. Now, basically the x bar of this data is going to be 19,000. 19,000 plus 8,000 is 27,000. 27,006. The sum of these numbers is 27,006 divided by, if I divide that by 6, I'll get 4,500. So 4,500 is somewhere over here, meaning that if I take is somewhere over here, meaning that half of, basically, let's say that halfway between these two numbers is 2,500. 2,501 point, for example, 75 divided by 2 is 1,250.875. 1,250.8, write it in black. 1,250.875. So that is that. So that if I add that number to, and halfway between these two numbers, 2,500, let me see, 2,500.75 plus 5,000.5, and if I divide that number by 2, yeah, I get 3,750.625. I get 3,750.625. Of course, that part is not very important, but now the mean of this data is 4,501, and it's somewhere over here. It is somewhere over here. Okay, so now the conclusion that we can have here, of course, it's not a complete conclusion, but what you can see is that basically as far as the mean is concerned, value wise, it's going to be moving on the number line. It's going to be moving on the number line between that lower limit and the upper limit of your observations, or between the minimum and the maximum of your observations, depending on the variations in your data. So for example, if you make this side weightier, then it's going to move to the other side. Make the other side weightier, it's going to move to the other side, somehow going to balance itself depending on the value of the numbers. But the location of that number on the number line is going to be a function of basically the overall value of the numbers on the two sides of the number line, starting from the minimum all the way up to the maximum. So it's going to move. But but the median of two numbers is basically always always the middle value, is always the middle point in the numbers. If you basically sort your numbers in an ascending order or in a descending order, it's not going to move. That means that your median is always going to be, the midpoint here is going to be the midpoint here, and it's going to be the midpoint, for example, here. So your median is always going to be, for example, in this case, if you were to calculate the median, what would you do? You would have basically 6 numbers over here, so you have an even number of numbers here. The number of numbers is 6. 6 divided by 2 is equal to 3, and 6 divided by 2 plus 1 is equal to 4. So the third observation and the fourth observation would be 3 and 4. The average of that would be 3.5, right? So that's exactly halfway between 1 and 6, which is the minimum and which are the minimum and maximum of your data. If you were to take, for example, the median here, what would you do? You have the 1 and you have the 15, you have the 1 and the 3000 over here. So the number of these numbers is going to be exactly 3000 numbers. So 3000 numbers is again a what would you call it? An even number. An even number, that means that if I calculate 3000 divided by 2, which is equal to 1500, and 3000 divided by 2 plus 1, which is equal to 1501, these two observations are going to be, if I take these two observations and take the, this is actually the 1500th observation and the 1501th observation, whose values happen to be exactly 1500 and 1501. So if I take basically the mean of these two values, 1500 plus 1500 plus 1501 divided by 2 is equal to 1500.5, which is, of course, in this case, it's supposed to be, actually the midpoint is supposed to be 1505, and this is exactly the median of your data, exactly halfway between your data. Again, over here, the number of numbers that you have is 10,000. So 10,000, again, 10,000 divided by 2 is the 5,000th observation and the 5,001th observation. And those values happen to be, in this series, is going to be 5,000 and 5,001. Now take the average of these two. 5,000 plus 5,001 divided by 2 is equal to 5,000.5, which is basically this number, which is exactly halfway between the minimum and maximum, and that's the median of your numbers. So in one of the examples that we did in the theory or in some exercise or whatever it was we were doing, we said that sometimes the value of the mean of your data is less than the median. Sometimes it's greater than the median, and sometimes it's exactly equal to the median. And that actually means something in terms of what sort of data you have basically, and you're working on, right? So then as a conclusion, let me just read the text that we have in the book, and then we can move forward with the rest of this topic. So it says that in a series, this you can think of these numbers as a series, for example, 1 through 3,000, 1 through 10,000, or 1 through 6, for example. In a series where the degree of variability is very high, meaning the numbers are varying, I don't understand what they mean exactly by the degree of variability, but I could say that I would say that, for example, the degree of variability here is not very high. But then over here, the degree of variability, you might be able to say that it's very high, or over here, you might be able to say that the degree of variability here is high. Or maybe even, for example, the numbers jumping around. For example, you get 1 but of course, when you sort your numbers in an ascending or descending order, then things are going to basically quiet down, but still, the numbers, if they were jumping around too much, then that would probably be described as a high degree of variability. I don't really understand what they mean by that. So it says that where the degree of variability is very high, the median is not a representative central tendency. Thus, the mean deviation above the mean calculated for such series cannot be fully relied upon. So the sum of the deviations from the mean, of course, you know that the sum of the deviations, for example, from the mean would be, suppose that you have some data over here, and suppose that this is your minimum and this is your maximum, and suppose that this is, for example, here is your mean, right? And so you have all of these observations all the way up to here. Now, this is the value of your mean, and the deviation of these observations from the mean is the kind of basic the distance that they have from the mean. For example, in the case of this particular observation, this is the distance of this observation from the mean. In the case of this particular observation, this is the distance of the observation from the mean, and so on and so forth. So when we calculate the mean basically the mean what do you call it? The mean deviation. When we calculate the mean deviation about the mean, what we do is that we take the mean, right? And then we calculate for each and every one of these observations, we calculate the distance of the observation from the mean, add all of those distances together, and then take the mean of that, take the average of that. And that becomes the mean deviation from the mean. Now, this happens to be, now it says that the sum of the deviations from the mean, the minus sign ignored, is more than the sum of the deviations from the median. I don't understand how that happens, but it seems that it happens. Probably if you test that idea, you will most probably get the same thing, and of course you will get the same thing, because otherwise they wouldn't have written it over here. I have never actually been in any sort of situation where I couldn't trust anything that I read in this book. I've never seen anything wrong in this book yet. And that's basically, I'm saying this based on reading all these series of books for like a year or so. So I can pretty much trust this book. So it says that the sum of the deviations from the mean, the minus signs ignored, is more than the sum of the deviations from the median. And therefore the mean deviation about the mean is not very scientific. Thus, in many cases, mean deviation may give unsatisfactory So let me start over. the sum of the deviations from the mean, the minus sign ignored, is more than the sum of the deviations from the median. Therefore, the mean deviation about the mean is not very scientific, meaning that it can is not very scientific means that probably, I don't know what they mean by that anyway. Thus, in many cases, mean deviation may give basically unsatisfactory results. Also, mean deviation is calculated on the basis of absolute values of the deviations and therefore cannot be subjected to further algebraic treatment, because you know that when you calculate mean deviation, for example, when you calculate the mean deviation about the mean, what happens is that, for example, you will get the sigma of f of I times the absolute value of x of I minus, for example, m divided by sigma f of I, right? So you can see that you're taking the absolute value of all of these distances, and when you take the absolute value, the algebraic sign is simply lost here, and so that's basically why they say that is basically it cannot be subjected to further algebraic treatment. So this implies that we must have some other measure of dispersion. Standard deviation is such a measure of dispersion. So now let's see what is standard deviation. Okay. Okay, so now about standard deviation and variance. So we have something here called variance and standard deviation. So it says, I recall that while calculating mean deviation above the mean or median, the absolute values of the deviations were taken. So we took the basically, for example, the mean deviation about the mean was simply basically all of these x of I minus, for example, minus m. We calculated all of the difference between each observation and the median of the data, and then we took the absolute value of that value, because we wanted to basically, we were only interested in the distance, meaning that, for example, if the median is over here, if the observation is over here, then your observation is smaller than your median, then x of I would be, for example, x of I minus m in this case would be a negative value. On the other hand, if x of I is over here, then x of I minus m is going to be a positive value, and since your observations could be all over the place, less than m and greater than m, we took the absolute value of that difference because we were only interested in the difference or in the distance. And then we basically multiplied this by f of I, meaning the frequency of those deviations. Meaning that, for example, suppose that relative to this x of I, you have 1, 2, 3, 4, 5, 6 observations. So then you multiply 6 by that value, and you don't have to write it over and over again. So that's basically why you multiply your f of I into basically this expression. And then since we wanted to, and then we took the sigma of this, we added all of these values together, and since we wanted to take the mean of basically all of these, all of such distances, we divided that by the number of all observations, which was basically n, or you could call it, for example, sigma f of I, the total number of all observations. You could take this one or this one. But basically in the formula we took the absolute values of the deviations. This is your deviation, and we took the absolute values of those deviations. Now the absolute values were taken to give meaning to the mean deviation. Otherwise, the deviations may cancel among themselves. So what that means is that for example, suppose that you have some x1 over here and you have some x2 over here, and suppose that x1, for example, is equal to negative x2, right? So you have these two observations over here related to your data. x1 is equal to negative x2. The exact same values, but only with basically this one is the negative of this one, or this one is the negative of this one. Now in this situation, this observation, if you add basically these two, if you simply calculate x2 minus m, and if you calculate, for example, x1 minus m, what happens is that this is going to be a positive value, and this is going to be a negative value, but both of them are, the absolute value of both of them is going to be equal to some value a, for example, and the absolute value of this is also going to be equal to some a, for example. So as far as the magnitude of these two are concerned, they are exactly the same values, because x1 and x2 are exactly at the same distance from m, only that this becomes a negative value and this becomes a positive value. And so if you add them together, of course they will cancel each other out, and then then the mean deviation, this part becomes 0, and so sigma 0 is of course equal to 0. So then the mean deviation you could actually end up with a 0. So it says that the absolute values were taken to give meaning to the mean deviation, otherwise deviation may cancel among themselves. So another way to overcome this difficulty, which arose due to the signs of deviations, is to take squares of all the deviations. So if you take the squares of all deviations and then probably take the square root of that, then you can take care of that problem. Obviously, all these squares of deviations are non-negative, meaning that any number that you have, whether a is a negative number or a is a positive number, a squared is going to be a positive number. So what that means is that all of these squares of deviations are non-negative. Now let basically x1, x2, x3, and so on and so forth, all the way up to x of n, be n observations, and x bar be their mean. So that's the mean of all of these observations. Then x1 minus x bar whole squared plus x2 minus x bar whole squared plus all the way up to x of n minus x bar Okay, so then x1 minus x bar whole square plus x2 minus x bar whole square plus all the way up to x of n minus x bar whole squared is equal to x of I minus x bar whole squared is equal to x of I minus x bar whole squared as I goes from 1 to n. right? We can write it with this notation, meaning that instead of writing all of this, or I think this is sigma. There has to be a sigma over here, but basically the sigma has kind of been forgotten. So I can write it as sigma x of n minus x bar whole squared as I goes from 1 to n. Now if this sum is 0, then each x of I minus x bar has to be 0. So if basically sigma x of n minus x bar whole squared as I goes from 1 to n, if this is equal to 0, then each x of so this is supposed to be x of I, of course. This is supposed to be x of I. Then each x of I minus x bar whole squared has to be 0. This implies that there is no dispersion at all. So this implies that there is no dispersion at all. And if there is no dispersion, that means that every x of I is equal to x bar, of course. At all, as all observations are equal to the mean x bar. As all observations are equal to the mean x bar. Now, if sigma x of I minus x bar whole squared, if sigma x of I minus x bar whole squared as I goes from 1 to n is small, this indicates that the observations are close to the mean x bar. This indicates that the observations x1, x, x2, x3 all the way up to x of n are close to the mean, x bar, and therefore there is a lower degree of dispersion. And therefore there is a lower degree of dispersion. On the contrary, or on the other hand, if this sum is large, there is a higher degree of dispersion of the observations from the mean x bar. Can we thus say that the sum sigma x of I minus x bar whole squared is a reasonable indicator of the degree of dispersion or scatter? So now based on this, can we say that basically sigma x of I minus x bar whole squared as I goes from 1 to n is a reasonable indicator of the degree of dispersion or scatter? Is that true? Let us take the set A of 6 observations. For example, let's take this set A of 6 observations. For example, you have 5, 15, 25, 35, 45, and 55. The mean of the observations is x bar is equal to 30. Okay, the mean is 30. The sum of the squares of deviations from x bar for this set is basically, if you calculate sigma x of I minus x bar whole squared as I goes from 1 to 6, for example, in this case, is equal to basically, then you can calculate 5 minus 30 whole squared plus 15 minus 30 whole squared plus 25 minus 30 whole squared plus 35 minus 30 whole squared plus 45 minus 30 whole squared plus 55 minus 30 whole squared, which is equal to negative 25 whole squared, which is equal to 625. 15 minus 30 whole squared is basically 15 squared. 15 squared is equal to 15 times 15 is equal to 225. 5 minus 30 is 25 squared is, I think, is 625. That's correct. Now 25 minus 30 whole squared is 25. 35 minus 30 is equal to 5 squared, which is equal to 25. 45 minus 30 is 15 squared is equal to 225. And 55 minus 30 is equal to 25 squared is equal to 625. So as you can see, these numbers are repeating themselves in this manner. Of course, as long as there is this difference between all of your observations, meaning that every observation you've gotten, it's like an arithmetic progression, right? Meaning that every observation, if you add 10 to it, you'll get to the next one, and then the same, some similar thing is happening in your or at least you can say that there is some sort of trend there is something that you can notice in the result. So, and if you add these numbers together, you will get basically 625 plus 625 is 1250. And then you have 225 is 450, and then you have 25, that's a 50, so that's 0, 15, 1, and that's 1750. Right, so that is the number that you get as that's the number that we wanted to use as a measure of dispersion of this data from the mean, right? Now, let's now take another set B of 35 observations and see what happens in that case. Okay, so let's see what happens there. Okay, so now let's take a look at another distribution here. And another distribution we have as the distribution B. Let me take a screenshot of this distribution. Okay, so now let's say that we have another distribution: 15, 16, 17, 18, 19, 20, 21, 22, all the way up to 45. So you have all of these numbers, like for example 15, 16, 17, 18, 19, all the way up to 45. So now if you have these numbers, now the mean of these observations is y bar. So the mean of these observations, is y bar is equal to 30. Okay, and of course the set that we had before, this set that we had here, the mean over here was also 30. Okay, this set over here, the mean was 30. Now note that both the sets A and B, so this they have called it set B, and the set that we had before they have called it set A, and both of these sets have a mean of 30. Now the sum of squares of deviations of observations from set B for set B from the mean y is given by, you have to calculate sigma basically x of or y of I minus y bar as I goes from goes from 1 to, for example, I don't know the number of these terms, 31 terms, right? So it's 15 to 45, it's 45 minus 15 is equal to 30, and plus 1 would be 31 terms. Meaning that 45 is the 31st number in this set. So that's the same thing as that is the same thing as basically 15 minus y bar is equal to 30 whole squared, plus, for example, 16 minus 30 whole squared, plus basically 17 minus 30 whole squared, plus all the way up to 45 minus 30, all the way up to 45 minus 30 all squared, which is the same thing as basically so here you go from basically 15 to 30, and then from 30 to 45, right? So when you go from 15 to 30, for 15 to 30 you will get basically 15, that's negative 15 squared plus negative 14 squared plus negative 13 squared plus all the way up to when you get to 30, which you will get 0 squared, because 30 minus 30 is equal to 0, so that's 0 squared, and then you have to go from 1 to 45. So 1 minus 30, for example, is, let me see, 15, 16, I'm sorry, all the way up to, you get to 30, right? And then you have 31, 32, 33, and so on and so forth. So 31 minus 30, for example, whole squared, plus 32 minus 30 whole squared, plus all the way up to 45 minus 30 whole squared. Now 31 minus 30 whole squared is equal to 1 squared. That is equal to 2 squared. That is equal to, for example, all the way up to 15 squared. And so what that means is that you have you have basically 1 squared to 15 squared. If you were to rewrite this part, that is 1 squared, basically negative 1 squared is the same thing as 1 squared. So, and negative 2 squared is the same thing as 2 squared. Negative 3 squared is the same thing as 3 squared, and so on and so forth. So you have 1 squared plus 2 squared plus 3 squared plus all the way up to 15 squared. And then you have over here basically 1 squared all the way up to 15 squared. 1 squared plus 2 squared plus 3 squared plus all the way up to 15 squared. That means that you have 2 times 1 squared plus 2 squared plus 3 squared plus all the way up to 15 squared. Which means that, and you know that sigma x squared, sigma x of I whole squared when I goes from 1 to n is equal to, okay, so now sigma x of I squared when I goes from 1 to n, and by that I mean that the sum of squares of, by this I mean the sum of squares of the first n natural numbers. You can find that using I don't know where exactly, but using the binomial theorem or somewhere in that area, you can find this formula as n times n plus 1, n times n plus 1 times 2n plus 1. I don't exactly remember where we got this formula, divided by 6. I think in arithmetic progressions or something like that. Anyway, in arithmetic progressions most probably. So then based on this formula, you can write over here your n is equal to 15. So you can write it as 2 times basically 15 times 16 times basically 31 divided by 6. And so that is equal to basically 2, and you get the 3 over here, you get the 5 over here, and then 16 times 31 times 5 is equal to 31 times 16 is 6, 18, 0, 31, 6, 9, 4 times 5 is equal to 30, 45, 48, 4, and 24, that's 2480. 2480. So the sum of all of these numbers then in the end becomes 2480. So that's basically the other set, basically starting at 15, 16, 17, 18, all the way up to 45. And the mean of the numbers was 30, the same as the other set. But over here we got 1750, over here we got, and the number of these numbers were like, I don't know, 6 or 7 numbers. The number of these numbers were like 31 numbers, and well, the number that basically the sum that we got here was 2480. So then Now, if basically sigma x sub I minus x bar whole squared is simply our measure of this dispersion or scattered about mean, we will tend to say that the set A of 6 observations has a lesser dispersion about the mean than the set B of 31 observations, even though the observations in set A are more scattered from the mean, meaning that in set A, these observations are, of course, more scattered from the mean. You see, the mean over here is 30, and of course, if you think about it, for example, 5 and 55, the two basically extremes, are much more scattered from the mean than meaning that, for example, here you get the difference between these two numbers is 25, here is 25. And over here, basically, these numbers are, the difference between this number and this number is 15, the difference between these two numbers is 15. So these are, well, if you think about it that way, basically these are less scattered actually. But we got this larger number for this set B. So now if sigma x sub I minus x bar whole squared is simply our measure of dispersion or scattered about mean, we will tend to say that the set A of 6 observations has a lesser dispersion about the mean than the set B of 31 observations, even though the observations in set A are more scattered than the mean, are more scattered from the mean than in set B. So even though we basically in set A the numbers are more scattered, for that case we got a smaller number than in this case, which the number was, for example, a larger number, 2480, and in which case the numbers are actually less scattered than the previous case. So it kind of doesn't make much sense. And from basically we can actually see that on a diagram, meaning that, for example, on set A, we went from basically 5 to 55, and the difference between each number is 10. So you get basically, if you can go for 0 and 5, 10, 15, 25, 35, 45, 55, or let's say 5, 10, for example, 15, 20, 25, 30, 35, 45, 40, 45, 50, and 55. So, okay, so now the numbers that we have in the case of the set A were basically 5, 15, 25, 35. So we had, this is 5, of course. We had 5, 15, and then we had 25, 35, 45, and 55. And the mean of these numbers were 30. The mean of these numbers were 30. And in the case of the other set, this was set A. And in the case of the other set, now in the case of the second set of observations B, we have basically all of these numbers like 15 to 45. So you can go from 15 to 45, 0 to, for example, the same scale I choose here. So 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, and we go from 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, and 60. And the observations that we had went from 15 to 45. Went from 15 to 45. 15 to 45 here, right? So so we will tend to say that, so if sigma x of I minus x bar whole squared is simply our measure of dispersion or scatter above mean, we will tend to say that the set of A of basically six observations has a lesser dispersion about the mean than the set B of basically, and here basically the mean is again the same number 30. This is your mean, and here this is your mean, and so we will tend to say that the set A of six observations has a lesser dispersion about the mean than B of 31 observations, even though the observations in set A are more scattered from the mean, meaning that you can see that these are actually more scattered around the mean than these observations. And we can see that basically in these two number lines as well. Thus, we can say that the sum of squares of deviations from the mean is not a proper measure of dispersion. Now, to overcome this difficulty, we take the mean of squares of the deviations. That is, we take the sigma f of sigma, basically x of I minus x bar whole squared as I goes from 1 to n. And then we take the mean of that, meaning that you divide that by the number of observations, as a quantity which leads to a proper measure of dispersion. This number, that is the mean of the squares of the deviations from the mean, is called the variance. So this number, we call it the variance, and is denoted by sigma squared. This is denoted by sigma squared. So sigma in the Greek language, there are two types of sigma. Let me see. There is a physics book where I had all of these things. Physics class 11 part 1, and then you have go into the PSA1, I don't know, appendices. Okay, so if I take a screenshot here, okay, so over here I have all the Greek alphabet, and just to well, we will basically practice this together later. But sigma, as you can see, is right over here. So this is uppercase letters. These are uppercase letters in the first column, and these are the lowercase letters in the second column. So you have basically this part over here, and then you have this part over here, and then you have this part over here, and sigma comes exactly over here. So sigma uppercase is written like sigma, and lowercase sigma is written as this letter here. So then we call this the sigma squared. Therefore, the variance of n observations, so just to sum this up, we take the sigma of x of I minus x bar, that is the deviation about the mean, and then we square it. We take the sigma of that as I goes from 1 to n, and then we take the mean of that. The mean of that is basically dividing the whole thing by n, and we call it sigma squared, and we call it variance. Okay, so and we call it variance, and it's denoted by sigma squared. Therefore, the variance of n observations x1, x2, all the way up to x of n is given by this formula. So you can say that the variance of n observations, the variance of n observations x1, x2, x3 all the way up to x of n is given by sigma squared. Sigma squared is equal to 1 over n sigma of basically x of I minus x bar whole squared as I goes from 1 to n. That is the variance of n observations. I don't like this color. Now there is one more thing which is called the standard deviation. We will talk about that in the next video.